Okay, let's get started. First of all, welcome everyone to Bioengineering 280A or Electrical and Computer Engineering 207A. So if you're there for one of those two, here for one of those two classes, this is the right room. If not, you're not in the right room. Okay. So, I'm Tom Liu. I'm being one of the instructors. This is Elliot McVeigh. So he's the other instructor. And then we have two TAs. Kishore, do you want to stand up? So this is one of your TAs. And Avanti, are you here? Ah, yes, great. Okay. So these are the two most important people for you for
Your
the
life in
course.
this course.
We're just like supplementary, okay? So get to know your TAs. They'll be posting a poll pretty soon to sort of see what are good times for office hours. And then I guess they'll be using a Piazza too, is right? So the main communication will be you can come. Professor McVeigh and I will stay after lectures for office hours. So if you have questions after lecture, you can ask us. And then the other office hours will be probably some in person, probably some Zoom, and probably hybrid as well with the TAs. And then you can post questions to Piazza. Okay. So any questions about that? All right.
Let me ask one question first.
Sure.
Those of you who are tuned in online, can you hear us and see my screen? Just give a thumbs up or something would be great. If
Yes or no?
I haven't seen anything yet.
Okay. Are we recording?
I think it automatically records,
Okay.
right?
I don't know. Yeah.
Yeah.
I don't know.
Let's see what they say in the chat here. Maybe somebody chatted. Yeah, we can hear you. Good.
Okay.
Perfect. Thank
Okay.
you.
So yeah, Professor McVeigh is going to give the first lecture, but let's just go over some logistics first. So I think we went over the instructors and TAs. One thing about Zoom is because we're on there are two different Zoom links. So for everything up through lecture 8, this is the link. And then we'll switch over to this link for lectures 9 through 17. And then uh, we'll update this in terms of what the project, I think this is for the project 1 and 2 presentations, but we'll update that. Also, everything is going to be recorded as best we can. So it will be posted on YouTube. And if for some reason the recording doesn't work, you can always go back to the previous year. The material is fairly similar from year to year. There are some tweaks from year to year. The one important thing is there is a scheduling conflict on October 8th. So we won't be in this room on October 8th. So that's going to be Zoom only. Otherwise, everything's going to be in person. And also, we'll try to broadcast live on Zoom. The only downside with Zoom is sometimes it's much better now, but sometimes the connection might go down. So just you have to take that into account. Let's see. Oh, there we go. Okay.
Yeah,
So we'll send out a poll later in terms of some people have a really good background in signals and systems and Fourier transforms. Others might need some review or some intro to that. So we will send out a poll later this week in terms of if there's any interest in sort of supplementary sessions. These will be more like there's already videos online that you can watch, and then so these will be more if you want to come and ask additional questions, sort of like additional extended TA office hours. But those I'll lead at least two of those probably. The required text is here, and it's available through this link, My Course Materials. And if you look at sort of the red shelf, I think you might see two options. Has anyone accessed this successfully? Yes, so it works.
It seems like you have access to everything, so if you opt out, will it go away on October 11th?
I think if you opt out, then it will opt you out of this book. I don't know you mean by everything? Yeah. So I think, yeah, I mean, my understanding is hopefully you can opt out of different courses. So I think the only thing to keep an eye on is if you don't opt out, they will charge you $50. Okay. But I think it's if you think you're going to be in this field for a while, then it's $50 and I believe you have lifetime access. So it's not a bad deal. Okay. There are some supplementary texts that you can get if you want to, and we might offer some chapters for that. Everything's on Canvas, and there's lots of supplementary videos on the channel and past videos. For grading, so it's pretty much going to be mostly weighted towards projects. So there's going to be two projects. The way we'll do the projects is one of the weeks, like week 6 or something, or week 7. there'll be project presentations, and then we'll also use the final exam period, that 3-hour chunk in finals week. So there will be 2 projects. There will be homeworks, probably about 6 or 7 homeworks assignments throughout the quarter. That's 20% of your grade. And then quizzes and class participation. We may offer, sometimes we'll use Canvas to do some pre-lecture quizzes. It's just sort of see if you sort of just help you remember the previous lecture. And then there might be some participation associated with the projects, like coming up with questions on other people's projects. Okay. But it's pretty, don't worry about it too much. It should be, even the lectures are pretty easy to do. Even the quizzes are pretty easy. They're just meant to make sure you were somewhat awake during the previous lecture. Okay. And then finally, we will be using a lot of MATLAB. And in fact, homework 1 will have the first MATLAB assignment on it. And we're using something called MATLAB Grader. So basically through Canvas, you can sort of do the MATLAB program, paste your code in, and then it will sort of evaluate it, give you immediate feedback. So typically you can do it as many times as you want, submit it as many times as you want. So as long as you keep trying, you should be able to get those MATLAB assignments done. The other thing you'll see on all the assignments is we do have a sort of AI chat GPT policy. Basically, use whatever you want, but you will be sort of asked to sort of describe what you did. And the TAs are sort of, their main task is as they're grading to look through sort of whether, you just, how you use the AI. Now, a word of caution, a lot of the problems are meant to be fairly simple. So you may spend more time using AI to get the wrong answer than just doing it yourself. So just be aware of that. And also you probably won't learn as much. So it's really up to you to decide how you want to use AI. We're not here to police it, but there's no restrictions on using it. And in fact, I think for the projects, we'll actually even encourage that you use it. Yeah.
Absolutely. You should become really good at using Claude or ChatGPT or anything to write code and check the code. And then if it doesn't work, figure out which part doesn't work. It will help you figure that out. And just use it like it's your amazing friend. Right?
Who will hallucinate once in a while.
Yeah, who is also an amazing liar.
Yeah, great
right?
liar, very convincing.
So they will convince you that this is true, but it's actually not. But
Yeah.
so are humans, right?
Yeah.
So,
and the last thing I'll do before I turn it over to Professor McVeigh is this is the syllabus, so you can sort of see now. Oh, this is actually not the view you'll see. So we got to go to view as student. All right.
yeah.
So if you're ever worried, if you're thinking about what's next, this tells you, and so you've got the lectures. This is important. If you are, I mean, everyone should just fill this out. It's really tied to financial aid and sort of federal regulation. So if you are on any financial aid or even worried about, you might as well just fill this out. Okay. I think it only takes a few minutes, but this is how the university handles that. Other than that, as quizzes and other things get assigned, they will be available here, and you'll also typically get an email through Canvas. So those are the project presentations and then the finals. So that's about it for course logistics. Are there any questions before we start the first lecture? Yes. Yeah, I think it's fine to collaborate. I mean, I think the TAs will be like, I don't know, was there a written collaboration policy last year? Do you remember?
We had to specifically state who we worked with and what their contribution was.
Yeah, I think on the homework, there'll be a collaboration policy. So if you do like work closely with someone else,
Which is fine.
It's just fine. Yeah.
Right. Yeah.
Yeah, it's fine. Yeah.
Collaboration is good. Yeah.
Yeah.
Are the projects individual or is it group?
Group. We have to do group because, we wind up with about 75 people left in the class, something like that, after the shopping phase is over. So we have teams of 3, and we might even have to go to teams of 4 if the numbers stay really large. But it's somewhere there.
Cool. Thanks.
Okay.
Yeah, and there'll be more information about projects as we get like probably around week 3 or so. We'll give you more information.
The one thing Tom didn't mention was because of the time constraints of presenting so many projects to the class, 1/2 of the class will present their projects in the first project for project number 1. The other half of the class will make videos. You'll make a 12-minute video that is a presentation of the project, and then we all watch it and grade the project. And then those 2 groups switch for project 2. So live presentations for one group at the end in the exam week, and videos for the other group. Okay.
Yeah.
That's-
And depending on what the enrollment is, we might tweak it things. So
Sure.
we'll sort of see how things are by week 3. But yeah, I think that's about it. Any other questions? Okay, so I think first
Sure,
lecture.
great.
Yep, thanks. Yep.
Thanks, Tom. So just to get a read of the class, how many people have used the Fourier transform before in some way? In a differential equations class, just raise them up really well. Okay, great. So we're pretty well versed in what the Fourier transform is. It's and linear systems are basic math we're going to use here, right? The other thing about the course, like a lot of the problem sets are in MATLAB. Historically, we've done them in MATLAB. When you go to do your project, the projects that get the highest scores or grades usually involve some kind of simulation or some kind of construction of a digital representation of an imaging device. And then you run it through various, features like what happens if I image something that's moving, or what happens if I image something that gets bright and dim and bright and dim, stuff like that. So you can do that in Python if you want. I think you guys are perfectly fine looking at that code, right? And so if you're purely a Python person, then that's fine, right? However, the problem sets that come at you, right, will usually have MATLAB code in them instead of Python. But nowadays, you just take that MATLAB code and you tell ChatGPT with 4 words, turn this into Python, and then whoosh, it just happens, right? You've entered a wonderful new world. You're cresting right at this time where every single one of you has an extraordinary coding team in your pocket. It's bizarre. I have no idea where it's going, right? Like, what do I tell my kids they should do? I have no idea. But okay, so we're going to start with a very general lecture just on basic imaging, right? And medical imaging in particular. But all of you have in your pocket usually an extraordinary imaging device, which is your phone. And the dimensions of the pictures that your phone can take and the spatial resolution of those pictures is absolutely extraordinary, right? So you go ka-chink, and it's like a 4K by 3K or 6K by 5K picture. Most medical imaging pictures are 256 by 256, 512 by 512, something like that. So much smaller data. They're essentially, I think, still all MRI is 256 squared, right? Except for maybe high resolution 70 neuro, they might do 1K by 1K. So you have a lot of experience now just in when you take pictures, like what happens, So I have this light and someone's running across my backyard and I take a picture with my camera. And so you can see all of the artifacts that are generated from motion or from low light or, or saturation, like too much signal, etc. But remarkably, these phones also have programs inside them that compensate for all this stuff to make pictures wonderfully easy to take. So, a lot of what you can do now, if you want to do imaging experiments, just do it with your phone. So this is one of those additional books that Dr. Liu mentioned, this isn't a required textbook, but if you see medical imaging in your future, it's not a bad idea to get this book. It's a very practical, physics-based imaging book, as opposed to Prints and Links, which is basically a double E signals and systems approach to medical imaging. This one is a physics approach to medical imaging in that, it describes in greater detail how the system is built, and the hardware behind it. Normally, you can find like an earlier edition of this book for about $50, right? If you just go on Amazon and troll there for a while, you'll get one. So our goal, right, is when you come out of this class, we're going to base all of our examples on either CT imaging using X-rays, right, or MRI imaging using radio waves, right? So those are the two modalities that we're going to use as examples all the way through this course. And we will give you enough physical insight into the creation of that signal, right? Whether or not that signal is an X-ray or a radio wave, and how that signal is modulated to encode spatial information. So basically, it's the basic physics of how you generate a signal. So we'll look at that. And then once we've got that signal and we take it and compute what our estimate is of the object that made that signal, right? That's the image reconstruction part, the math or the inversion part of this. So now you've got the image in your hands and you ask a very fundamental question, is like, is this image any good? Like, is it a good representation of the object? How precisely am I representing the object? Am I within 20% of the truth, or et cetera? And then does the picture look any good for a clinician who's going to look at it and make a call, right? So, and then there you have things like spatial resolution or sharpness of the image. Is it a blurry picture or is it a sharp picture, right? In my early days at Johns Hopkins doing cardiac imaging with magnetic resonance, we came up with this new technique for making dynamic images of the heart, brought down all the bigwigs from cardiology to take a look at it. So we're all standing around the MR. There's a grad student in there making a picture. And it comes up, and one of the senior cardiologists looks and goes, "Oh man, that's amazing. Can you like focus it?" Right? So it's just, there it is. It's like, this is kind of blurry. I would like it a bit sharper, right? So what is that? How do you quantify if it's focused or not, if it's out of focus? And then there are things like signal to noise, which is very fundamental trade-off usually in imaging. And that's, I can image for 4 hours and get a lot of signal and average out the noise, but I've imaged for 4 hours. So that's costly. The object might have moved, the object might have died. And what is the trade-off to get high signal, low noise, right? In X-rays, if I'm making an X-ray picture and I decide, you know what, I'm going to use twice as many X-rays on this next picture, and I do that, the signal to noise goes up, right? Sort of by the square root of the number of photons that I used. However, I've now subjected the patient to twice as much radiation. So there's a trade-off here, right? I can't just keep raising the amount of radiation that I'm using to get better and better pictures. So what are those trade-offs? We'll look at some applications, specifically like cardiac applications and MR. Tom will look at things like blood flow, neurological function. You can image with MRI. And also the ability to just have a common sense approach. Like when you're done, and we've gone through all this stuff, you should be able to, when a picture comes up from an imaging system, you should know the questions to ask. Like is this optimized? Is this any good? right? And, you know, we're the kind of the engineering side that produces the pictures that are shown to clinicians, to radiologists. And so it's our job as engineers just to make those pictures the best that they can be. And the evaluation of how good they are comes down to if this person actually does have the disease you're looking for, what is the probability you will find it in this picture? A human looking at the picture will find it, right? That's the basic sensitivity of detecting that disease, right? There is also, how often is it going to happen that a very experienced radiologist looking at this picture will say, yes, this person does have the disease when they do not have that disease, right? So that's a false positive call that human has made, right? And the picture that you made could have had an artifact in it that pushes that person into believing that there is a disease there, right? So the basic structure of everything we're looking at is we have some object, and in this case, it looks like a plasticine model of somebody's brain inside their skull, right? The object, and we have an imaging device. And so the object either radiates some signal. In MRI, the object actually radiates with radio frequency energy. So you do something and the patient goes, it becomes an RF source, right? That's what's coming out of the patient. And you put these antennas up next to the patient and you see how much radio frequency energy is coming out of the patient. It's kind of cool, right? And so that's the source of the signal. In X-ray imaging, it's much simpler. I have a bright light, I shine it through the patient, and I create a shadow. And so my signal there is that shadow. And we'll see in CT, you make multiple shadowgrams at different angles, and you reconstruct the object. So using that physics, we wind up with a set of floating point numbers on some kind of array, right? It can be a 3D array, 2D array, whatever, and it's our measured data. You go in, you can manipulate that measured data to reduce noise that exists in there that you know is there, to reduce artifacts, and then submit that raw data to a reconstruction algorithm and produce a picture, right? And that representation of your true object is what we're now going to look at. And we're going to evaluate whether or not this is a decent representation of that object, right? So this guy, Joseph Fourier, came up with a mathematical formalism that pervades all of engineering and science, right? If you know anything when you come out of school, of any school, you should know what Joseph Fourier did, right? Because everything from quantum field theory in physics, like the highest, most complex physics you can imagine, it uses Fourier theory all the way down to, you know, how does a bar change its temperature as a function of position when I heat one side and not the other, right? So basically, the thought or the big concept behind this is if I have some kind of spatial pattern of signal or temporal pattern, but let's just say for this course, we're saying we have a spatial pattern of signal, and that signal gets high, and then it gets low, then it gets high, then it gets low. So it's basically just a set of stripes, right? Or here, top hats. This signal can be represented as the sum of very simple signals, which are sine waves and cosine waves, right? So these are called the underlying harmonics of what is contained inside this signal. And when we look at those harmonics, here's one that is a sine wave at frequency omega. In this class, the frequency is usually in space, so it's radians per meter, right, in space, as opposed to cycles per second which is like a frequency. If we were talking about music and these sine waves were like a musical note, then it would be cycles per second. For us, we have a picture on this carpet here, and I look at the physical changes in signal as a function of position. Then we have cycles per meter, right? Is how we're going to build up that picture. So if I have this primary harmonic here, which, as you can imagine, the peaks of this primary harmonic are the same distance as this signal we're trying to create. If I add up these harmonics and we say that we're changing the amplitudes go down as the frequency goes up. So I have omega, 3 omega, 5 omega. And I'm just going to add these together. So here's the primary, and then I add the primary to this guy. I get this signal is the output. So now I have a more complex signal than a primary sine wave, right? It's got these sort of ears on the edges here. It's not a flat top yet. But then I add a higher frequency and I change this to closer to a flat top. And then as I go to infinity, the amplitudes get smaller and smaller, converges actually, so I don't have infinite power. And the frequencies go up and up and up until finally I can make as close as necessary to this sharp function. As we add higher and higher frequencies, these are getting higher, I get sharper and sharper edges and corners on the function. So that's something to carry with you, and that is the high frequencies that are used to build the object are the things that build sharp edges and sharp corners and sharp points and things like that. You need the high frequencies to do that. To build signals that vary, in a very slow manner, say I'm imaging a liver and I say that one half of the liver is bright and the other half of the liver got darker. So it's a very low frequency signal. That's almost over the whole field of view of the image. As opposed to a sharp edge, it's like a large change, but a slow change, right? So it's the balance of these low frequency signals with the high frequency signals. So this is the fundamental equation that describes what these amplitudes here, how the amplitudes, and also I can also shift the phase of any one of these if I want, just push it left or right a little bit to add a phase shift. So that's these things. This is in 2 dimensions. That example was 1 dimension. But the primary mathematical structure that you're going to use in this class is in this equation right here. If you go home and talk to ChatGPT about, hey, can you describe the following to this equation is what you want to get really, really good at, right? At understanding what this thing actually means, right? And so you have an object here. This is the function is our picture, okay, in this example. So let's think of some simple pictures. One simple picture would be everything's dark in my field of view except a circle in the middle, right? That's sort of a fundamentally simple image. It's a circle that's all got a constant value, and then the background is 0. So this function would just be 1 wherever that circle existed, and it would be 0 in the background. And so that would be a simple function. A complex function would be a photograph of the, Manhattan skyline, taken at night or something. So you have many, many objects in there and edges and, peaks and things like that. That too could be represented by different values as a function of position in your field of view, right? When you take this integral, which is the Fourier integral, where this function, it has unit amplitude. It's just a 1, right? But its phase changes, right, as we run this integral over the image. So we're running the integral over dx and dy, right? And then as we change x and y, the phase of this function modulates, right? They're basically just sinusoids of different frequencies and phase. And when you run this integral, so we fix u and v right here, and so that's fixed, and then we get a value for those specific spatial frequencies found in this image, right? We'll go into the nitty-gritty details of this and do examples and stuff, but this is fundamentally, if you're going to understand anything, this is the equation to understand. You can then take this function, which is your set of harmonics, and apply an integral that is the inverse Fourier transform, which has exactly the same argument here, except the negative is now positive, and reconstruct what this image is. So they're pairs, right? They're called conjugate pairs. So this space here, we'll call it equally throughout this course. We'll either call it Fourier space, we'll call it K space, because we'll see in MRI you usually use KX, KY for spatial frequencies. Frequency space, they're harmonics, they're modes. In physics, they call them modes, right? So that's it. So we'll look at a brief history of when X-ray imaging began. And in 1895, this guy, Wilhelm Röntgen, who was at Würzburg or something, he was in Germany. He was doing an experiment where he was illuminating a gas in a tube by applying high voltage to either end of the tube. And he accidentally observed that a fluorescent screen, a phosphor screen that was sitting over it in one corner of the lab, when he activated the tube, it glowed, right? So he's looking at it going, what the heck? So he turns the voltage off, the phosphor stops glowing, turns the voltage on, the tube lights up, and the phosphor starts glowing, right? It's like, huh. So he realized that something was coming out of this tube that was exciting a fluorescence in that phosphor, right? And he called them X-rays because he had no idea what they were, right? So he said, that's an X-ray. And within a couple of years, this is like publish or perish, these X-rays were being used in medical images, like within like 4 years, right? So they had made X-ray imaging machines. And Marie Curie was part of that, et cetera. Fast forward 50 years, nuclear magnetic resonance is discovered purely in physics labs by Bloch on one coast, Purcell on the other coast. Hounsfield uses this NMR signal, uses the X-ray signal to create a CT scanner in 72. And like a year later, Lauterbur makes the practical version of the MRI imaging technique. And, in the early 70s, we go on to doing clinical imaging. This is an early X-ray picture in the same year that he discovered it of his wife's hand here held up where you excite the phosphor, but you put essentially a photographic film there such that the phosphor transfers an image onto the photographic film, right? And so this is like a X-ray of her hand with her ring, her wedding ring, I guess there, right? So it's one of the first X-rays ever taken. Didn't take long to get the Nobel Prize back then. 5 years after discovering, he got the Nobel Prize. It was a big deal. He lived to the ripe old age of 77, right? Doing all these experiments with X-rays and stuff like that. Marie Curie, on the other hand, who discovered radium like just a couple of years before this, and there's a lot of radiation coming from the radium, and they did many experiments, and they would put the radium in their pocket and stuff like that. And she actually died of cancer, so just from the dose of all this radiation. They didn't really understand the dose back then, but these guys seem to get through okay. So how do you make an X-ray image? Again, we have a source, of X-rays over here. So it's just like an X-ray light bulb. So you're going to apply a voltage, right? In fact, what happens is electrons hit a target and X-rays come out of your X-ray light bulb. And you put a little hole, you encase it, right? And just put a small hole such the X-rays emanate from a little square. And so with this flashlight, we're going to illuminate our patient, right, with that X-ray source, and then we'll either detect the X-rays that pass through the patient, right, here, or those X-rays will get absorbed within the patient and cause contrast, right? You know, if you have any radiation source, you've like laser pointers and stuff, you put it on your finger, you can like press it and you can see the light coming out of the back of your finger. So the light actually gets through your entire finger, right? However, when you look at the light that's coming out of your finger, there's no details there, right? It's because those photons have interacted with matter thousands of times getting across your finger. They're just reflecting all around inside. X-rays, on the other hand, like 50% of them are just going to pass right on through you, right? Without being disturbed at all, without getting bent or scattered off. 50% of them will hit usually an electron inside some atoms in the sample and will get completely absorbed or scatter off at a high enough angle that they don't get detected over here. Okay, so a large fraction of them, of the X-rays that hit something inside the patient, hit an electron inside the patient, go off at an angle that's quite large, so they don't hit the detector. So they're essentially eliminated, and that's what causes the contrast. You get places where a lot of X-rays get through. For example, in this patient's lungs here, where you see there's a lot of essentially X-rays have hit the film target here, so it goes dark. Whereas in the bones, a lot of X-rays get absorbed at the bone, and so not many X-rays hit that, and that when you look at the film, it comes up more bright. Early versions of how this was used medically. Here's I forget the year of this. I should have put the year down here, but obviously it's pretty early, right? It's like 1910 or something like that, where he's got this big voltage generator, X-ray generator right here is generating probably a set of X-rays that are going all over the room. And the patient is holding a film screen cassette at their chest, right on their chest. And so the X-rays are passing through the patient from their back and hitting the target here and creating an image, right? So that's early clinical chest X-rays, right? One of my favorite worst applications of X-ray imaging were these things called, I forget, pedo something. Anyway, what you would do is, and this was in shoe stores from the 30s, 40s, 50s. In the 60s, they started banning it. And then basically there was a few left in the late 60s. But you would go in and try on a new pair of shoes. You put your toes and your feet inside the shoes, and then you plug them into this thing, and there's an X-ray source down here. Turn on the X-ray source, and it hits a phosphor screen right at your face here. And you can look at your toes inside the shoes and wiggle your toes and go, wow, that fits just right. It's perfect, right? And in the meantime, you're getting like 500 times the background radiation of, just existing in life. This poor guy, the salesman, is doing this all day, right? So the customer goes in, you get one good dose, right to your head or something. This guy's standing over here, he's helping them all day, it's not good. So these people had a lot of health issues eventually. But everybody made these and they were very profitable. So here is a modern X-ray setup where we have a source of X-rays right here, right? This thing here is like an X-ray light bulb. It's going to shine X-rays towards our patient who's standing here. And then this whole thing back here has a detector behind it. And normally, as we'll see with this, that detector can move up and down to image different parts of the body. He's looking with some consternation at this cup full of something, right? So this is a milkshake, but inside that milkshake is barium sulfate. And so it's a really thick, gooey, white, viscous stuff. Sorry. And he's going to drink it. And then as he drinks the barium sulfate, the X-ray source here is going to track the swallowing of that stuff down in its esophagus to try and look for irregularities in the swallowing motion in the esophagus for a lesion that's there, right? You might have some cancerous thing growing on the side of your esophagus and it will show up in this scan. It's called a barium scan. And this is called a contrast agent. And the contrast agent is put in there to absorb a lot of X-rays. And barium, because it has a high number of nucleons, it's like Z number is, I want to say 38, but I don't know, it might be 57 or something, but it's got a lot of nucleons. And so the lowest energy level of the electron that is tightest to that nucleus, the K level electron, it takes a lot of energy to knock that thing out. It takes about 35 kilo electron volts to knock that thing out. And that matches the radiation that's coming out of this thing. And so the barium is a really good electron or X-ray absorber, right? And so that's what causes the really high contrast. And we'll see you can also inject iodine into a patient's vessel as a clear fluid. And when you inject that and you take an image, you see great contrast between the vascular structures and the background. So that's called a contrast agent used in X-ray imaging all the time. And an MR for that matter. Excuse me. So here's a chest X-ray. So this is a single shot, just like we showed that graphic of a patient standing in front of a detector, like 10 feet away is the X-ray source, boop, and you take one picture of this person's chest. And you don't have to be a rocket scientist to see that this is abnormal, right? And the reason you can see it's abnormal is people are generally fairly symmetric, right? There's a lot of things about humans that are midline symmetric, right? So this side of your brain and that side of your brain look pretty identical. This lung and this lung. Liver, that's a problem. Heart also is like on one side, but many things are symmetric. And so it's like a control. You're your own control. You look, especially in brain imaging, you look at one side of the brain, the other, and go, well, that's something strange there. That thing shouldn't be there. So here you can see that there's, something absorbing a lot of X-rays. So the spine absorbs a lot of X-rays. The bone absorbs a lot of X-rays. So you get this brighter signal. And then this stuff inside the lung is probably fluid, right? That is building up because this patient has pneumonia, right? And so that inflammation you can figure out right away. So if you go into the hospital, and you have a bad cough or whatever, they can tell you, man, we got to get you on antibiotics now or whatever, because this thing doesn't look good. Here's serial radiographs in the same person as COVID-19 essentially gets worse in this patient, right? So we start with relatively clear, although you can see there's some weird high contrast up here. And then it gets all sort of smoky and foggy as the fluid builds up. And then it gets really foggy, right? So you can't even see through the lung, right? And in the early days, this is one of the early papers that came out looking at early COVID patients with CT. And so now this is a very thin slice of lung, and brightness is fluid in the lung. And so this is the patient when they first present. I forget what the time is. 12. Oh, day 15. There you go. Sorry. Day 5, day 15, day 20. Oh my God. So when I saw this, I was just like, damn, give me that vaccine. I don't want any part of this virus because it is bad, right? So it's really, really terrible. So here is X-ray image. This is, again, a single projection image, which is called an X-ray mammogram. And it essentially, the X-rays pass all the way through a compressed breast. Okay, so normally there's a compression plate. You compress the breast as far as you can so it's as flat and thin as you can. And then you shoot X-rays down onto a high resolution grid. And so this is the picture. Inside this field of view here is a tumor. Right? And so the question is, as a radiologist reading mammograms, you've got to look at this picture and decide, is it positive, negative, right? This job is super hard, right? And I did it for 3 days at Hopkins with a resident and then the senior faculty person to get experience and see what. So we were going to do some. This is way back before AI. We were going to do some auto detection and help filtering and stuff. It was tough, and they were looking, and then the deal is you go, okay, it's positive. And so the patient goes and gets a biopsy, and the biopsy comes back negative. And like, oh, sorry, right? Because now you've gone through this whole biopsy procedure for no damn good reason, right? So this is a tricky call. This is called tomosynthesis, where you reduce the amount of signal from either side of a selected plane, right? You either blur it out so that it makes no detail, or you zero it out. And so now this structure here, which we didn't really appreciate, I certainly didn't appreciate when I was looking at this original thing, now has a classic shape. It has these spicular sort of tissue things that run away from the primary. And so at this point, it's pretty easy to call that positive, right? So this is still an ongoing development in imaging, is how to do mammography really well. As you can imagine, there are tens of millions of mammograms out there with, outcome data, right? So, so I've got a mammogram from like 1991. I know what happened, whether that person went on to get cancer. And so training up AI on this stuff is a great idea, right? So that you have a resident sitting beside you who has seen a million of these, right? And knows. So there was a question back there. Yeah. They're the same breast, and however, they're not exactly the same image. The actual collection of the data was different in the sense that this is not a full-on projection through the whole breast. There was basically you move the source and the detector such that you defocus things around a selected plane. Okay, and that way you can take the whole breast, which might be after compression here 1.5 centimeters, and instead of looking at that, we're going to look at 5 millimeters, right? And so it isn't just computer analysis of this picture going to this picture. It's actually a different way of collecting data from the breast. And then there's a whole field of CT imaging for the breast, so making computed tomography scanners just for the breast. And then if you're in a high risk category of, genetically, you have high risk for breast cancer, it's also recommended that you get MRI, because MRI is very sensitive for picking up tumors. However, it has a high false positive rate. So it'll highlight things that actually aren't malignant tumors and you think they are. So you have to sort of balance these things out. Oh, I hope this is a movie. Yeah. Okay. So this is a X-ray image. So I have a source above the patient. Below the patient is my detector. They're lying on a table. Okay. And so here's the ribs. You can see, and this is the outside of the patient. Here's their ribs going through the plane. This thing here is a plastic tube. It has about a millimeter diameter, a couple millimeter diameter hole. It's a plastic tube. And what we've done is we've cut a little hole down on their thigh, the inside of their thigh, and opened up a vessel right there and put the plastic tube in the vessel and just keep pushing that tube, right? Just keep pushing like meters, right? And it goes up their aorta, it arches around their aorta and comes down to the root of the aorta right above the heart, okay? Who do you think would invent this, right? It's crazy, right? Just pushing it in. And I look at it, and then what you do is you take the end of it and so at the root of the aorta, you have two big holes coming out of the root of the aorta, and those two chambers go to what are called your coronary arteries. So you have your left main coronary artery and the right coronary artery, and so they come off, right? So they're basically, when you're sitting in there, you're down at the root of the aorta, there's a big valve here. Above the valve, you look, there's two holes, right? This guy gets plugged into one of those holes. Like, you just like goof around, play around until the thing's going this and like, go, oh, it's locked in, right? So it's plugged in, right? And then what you do is you rear back and you inject contrast through this plastic tube right into that coronary artery, right? And this is what it looks like when you do that, right? So you're making a movie now. You're just taking X-rays at 15 frames a second while you're injecting an X-ray contrast agent, which causes a shadow because it's absorbing the X-rays. And it's only doing it in the vascular structure. And so you have this amazing picture of vascular structure, right? So about 1.5 million of these pictures are done every year in the States, more even, right? And that's because people show up in the emergency room and they have chest pain, clutching their chest. They're like, oh, and they have running down, they've got pain in their jaw. You're like, okay, you look like you're having a heart attack. And you go to the cath lab and they do this. And then they look and say, is there a problem in your vessels? And you can see this person, it's not horrible, but see how it's a little bit more dim right there? That would say that that vessel is narrowed down at that point and blood might be having a hard time getting through. So this is like dynamic, high resolution X-ray imaging. You're only getting one projection. This isn't 3D imaging, right? It's just a projection to the whole thing, but it's pretty damn cool. And this is the iodine contrast agent. Yes? So the question is, how does the X-ray get through the bone but doesn't go through the contrast agent?
Yeah.
Okay. So the X-ray has a much higher probability of getting stopped in the bone than it does in, say, soft tissue, like muscle or fat. And so that's why the bone shows up as a high contrast object. The probability of it getting stopped in the iodine, because it's such a high concentration of iodine in the vessel, is much, much higher than even bone. And so that's why it looks like a very high contrast object, because a very large fraction of the X-rays are getting stopped by the iodine. And it's because iodine has a large Z number, right? And the K edge electron is much closer to the energy of the X-rays that are coming through here. And it has a much higher ability to stop the X-rays that way. The cross-section of the interaction is higher, right? Okay, but you can see, like, you can ask there's some simple questions you could ask yourself as an engineer, an imaging engineer, and say, hey, look at look at that vessel. Let me stop this thing. Look at this thing coming down here, right? So it's a perforating vessel that comes off the main coronary artery and goes into the muscle, right? And so it's perfusing the muscle, right? So what is the dimension of that thing? Right, I'm looking at it, I could zoom it up, and look at the pixels and say, just how wide or how narrow an object can I detect with this system, right? Eventually, if it gets small enough, I won't have enough iodine in there because it's just too small. So I won't be able to see it, right? Right. This is not Jack Daniels. Okay. Any other questions about this? This is one of my favorite imaging techniques. It's done a lot. Oh, you can also see like when the injection happens, see that there's a little puff coming back. So that's when you're pushing it in, some of it comes back out the back end and goes into the aorta, and then it'll get, when the heart beats, it just gets pushed away. And also you can see if we're at an angle where the vessel's coming at us, so it's very, now we've got a lot of iodine. You can see it gets very dark, right? Because the vessel's coming right at us at that point. So this is what the setup looks like. We have the X-ray source here. We have a detector here, and it's all sitting on what's called a C-arm. And so I can, as a physician, I can angle that C-arm around to take a projection through any angle I want through that patient, right? So basically you control, this would be a straight up called AP view where you're just coming through the back and hit up the top. But I can angle this thing such that I get a better look at the coronary vessel I'm most interested in, right? And so you just move that around. Those of you who are skipping ahead in your mind can think, hey, well, if I can take a picture at any angle, why don't I just like make the thing move and take a whole 3D picture, right? You can do that, right? And that is done. Okay, so the history of CT is amusing in some ways in that this guy, Johan Radon, I forget where he was. I think he was in South Africa or something. He was a mathematician, and he came up with the mathematical framework of tomography, how you Okay, can you guys hear me now? They're all bailing. They're going out.
Yeah.
Yeah, you can. Thank you very much. Great. All right. Thanks for the update. Okay. And then in 1963, this guy, Alan Cormack, uh, he published uh, a paper in which he shows that using X-ray projections, you could reconstruct an object, right? And he didn't cite his work at all. He just reinvented it, right? And then Godfrey Hounsfield, this guy here, experimentally in his lab, he builds a system in which he actually makes a CT scanner. It's a very sort of basic CT scanner, but comes up with a way to take these data and back project the images. And he doesn't cite this guy either, or this guy. So, yeah. Say again? Oh, okay. Thanks. Da-da-da. All right. Now is everybody good? All right. Okay. And well, the Nobel Committee gave the Nobel Prize to both these folks, even though they didn't cite each other. And it turns out the Hounsfield story is kind of interesting because he got to play in this lab on a technique that looked like it was, not going to go far because you need a lot of radiation and a long time and lots of math and everything to just make a simple picture. But he worked for EMI, and EMI at this time, this is like in the late 60s when he was setting up this lab. At that time, they owned Capitol Records. And through the 60s, Capitol Records made a ton of money, right? And the reason they made a ton of money is they own the copyright for all the Beatles songs, right? So these guys are flushing cash, and his lab is, he can build whatever the heck he wants. So interestingly, Paul McCartney, John Lennon writing songs leads to CT. So the basic principle of what's going to happen here is that if I have an object that has some details in it, so this is kind of like that simple image that we talked about before. Excuse me. Let's say I have a background substance, which is, perspex or a plastic, right? So I just make a plastic, volume. And then inside that volume, I drill out 2 holes, right? And inside those holes, I just put air, right? And then I drill out this hole, and inside that hole, I put that barium stuff, right? So it's high contrast material, right? So now I've got a trivial image. And I ask, if I was to shoot an X-ray, if I had a beam of X-rays, and they were going to go vertically down through my object like this, right? And I shot 1,000 X-rays in, right? How many would get through? Well, a lot of those X-rays would get absorbed by this plastic stuff, right? But there's a hole here, so there's a chunk of air through which none of the X-rays will get absorbed. They'll just go straight through that, right? And so when I look at the signal, just the count of number of X-rays I see, I get a higher number of X-rays depending on the line integral through that circle, right? So however long that segment is, I'll have increased my number of photons that come through, right? And then if I move over here and I now have an X-ray source here and shoot it through my object and have a detector here, absorbs down to the baseline here. So if I just go through the plastic, I get this many photons here. This one, if I go through the plastic, I get a reduction in the number of photons because as it's going through the barium, a lot of photons get absorbed, and therefore I get a reduction in the number of photons hitting my detector. Okay. And so that's the color scale here you can represent as the attenuation of X-rays. Bright means I attenuate a lot of X-rays. Dark means I attenuate fewer X-rays or none. So hence, this signal, I transform this signal into, brightness and darkness, but I can't position it up and down. It could have happened anywhere along this line, right? If I look at this signal, I don't know vertically where this happens, right? So let's take that signal and we'll just say, well, this could have happened anywhere up here, anywhere along that line. So I'll just say along this line, I get a reduction by this amount, and therefore I plot it as a darker column, right? And so now I have a simple image in which I have bright columns here where I got a lot of X-ray absorption, darker columns where I had less X-ray absorption. And then the baseline is here. So all this tells us, this projection is that there's something up in these columns. We don't know anything else. However, if I then take another view, if I either rotate the sample or I rotate my source and detector, to a different direction and I get new data in that direction, I can project this same thing back in that direction. And when I do this at multiple angles, I start seeing a collection of pixels or points at which it looks like I have lower X-ray absorption and a collection where it looks like I have higher. And as you can imagine, as we go to thousands of projections at smaller and smaller angles, I can reconstruct what's actually in there in the two-dimensional space, right? So the detector geometry that's used in X-ray CT, this was the original geometry where you had a source and that source would slide along across a straight line and cause a projection through the patient, right? That took a long time because you had to slide your source along and then you move the projector and slide your source along again. It took many minutes to take your data. That was replaced in the, I guess, early 80s, I want to say, by a single source that made a fan beam of X-rays. So now I have a light bulb, I put a little hole, and the X-rays come from that source. And all of my detectors pick up the data simultaneously. So now I can go poof and get a projection across all those points. And then in the 90s and aughts, people started stacking these together. So we have this basic detector thing, which has like a single row of detectors, and you have a CT scanner in which you have that single row of detectors. But now let's just stack them up one on top of the other. So now I have like, if this is 256 in that direction, I could do 256 scanners, right? It started out with 16, went to 32, 64, and then boom, to 256. Canon has a system now that has 320, detectors in this direction, right? So basically, this is a two-dimensional picture now that you go poof, and you have a two-dimensional projection through the patient. The geometry of a CT scanner is I have a source of X-rays, I have a detector over here, and it's on a gantry that can spin. And so my source and detector remain, with respect to each other, fixed. However, they rotate with respect to the patient. So they get different angle views through the patient. Siemens has a pretty cool system where they have a source and detector that's at right angles to the original source and detector. So they basically have two scanners running simultaneously in there. And that doubles your speed of imaging or cuts your imaging time in half. It's pretty cool. The scanner looks like this. What time are we at? We're at 15. Okay. Looks like this from the outside. This is about 65 centimeters, something like that. It's a donut with that. And then all of this detector business is inside here. It rotates at a fairly high clip. So it rotates once every 250 milliseconds, so 4 times a second. It's a lot of mass to rotate it 4 times a second. So it's built by companies that make big machines, big iron, like General Electric, Siemens, Philips, Canon. They, and then the other thing you can do is you can start this thing spinning and then just push the patient through your scanner such that you get an entire image of their whole body in a couple of seconds, right? If you want to do that. So this is from our scanner in the Jacobs Hospital, just downloading the data. There's 256 detectors in this direction. There's 892, about 1,000 detectors in this direction, right? And then for each angle, you take a picture, and that's a projection through this patient. So if we stop there, you can see, let's stop here. So this is their diaphragm here. This is the silhouette of the heart. spine is here, this is an arm, this is the side of the patient here. And then as I move, I get different angular views through the patient. If you look at this view, we have our source. This is like a horizontal view. The source is over here, detector's over here, patient's lying here. It's a long pathway from all the way on my right side, all the way through to my left side. Right? That's the patient's longer in that direction than they are in the AP direction. And you can see how this gets kind of hashy. So if I look at the signal smoothness here and the noise, I sort of have a noise level. And this noise level looks like it's gone up by about 5x, right? And what's happening over here is the path length through the patient is long enough to actually almost take out all the photons. And so now we have a very uncertain measurement of how many photons we've got because we're going down close to zero. Okay. This does happen a lot in CT because we want to image at doses where you're right at the limit of what you can detect, right? And so the signal that's shown here is not a shadow. As you can see, it's bright where CT is being absorbed a lot. So if we go back to you see it's bright in the central zone where you have the spine. That's because what is displayed here is actually the ratio of the number of photons detected at the detector divided by the number of photons detected at that detector when nothing is in the scanner. So you take everything out, make an exposure, and you get a number. That's I0. And then you put the patient in, make an exposure, you get ID, which is smaller than I0, right? Because some stuff gets absorbed. You take the log, we'll see why. You take the log of that, which would be a negative number, right? Because it's between 0 and 1. So you put a negative there, and that's the brightness. Okay? And that's actually what's used to make the pictures. So this is like a really early CT scan. Here's a modern CT scan, 512 by 512 matrix, and you can get that in 150 milliseconds, whereas here it took, 20 minutes to get this back in the. But these people had faith. That's the great thing about inventors, people who love what they're doing. It doesn't look good, right? Because it's so expensive, tons of radiation. Image looks like really weird, but they have faith and they wind up over here. But the thing is, if there was a tumor in here, you would see it, right? You would see some kind of distortion, whereas on a plain film, you would have no hope of seeing it. And so they kept going, made many, many beautiful pictures with CT. We'll just do, oh, we're done. We're at 12:20. We'll pick it up here next time. And then we'll get into discussing the quantitative definition of image quality and stuff like that. Hi.
Hi, all right, I've got